Okay, welcome to the 24th class meeting. First, I apologize for the late announcement about the last Wednesday. So I originally planned to record the class meeting 24, but I was not fully prepared for it. These days, I'm struggling with Gemini AI assistant to write not only the class handouts, but also some research paper. And it seems that due to the explosive use of Gemini and Nano Banana recently announced, it seems Gemini suddenly become very dumb. And I got really actually angry these days. It was okay a week ago, but suddenly it became very dumb during the week. Anyway, so I wasted a lot of time to prove something, and it turned out that Gemini was hallucinating. So I'm not that happy right now. But anyway, this document is kind of proofread by myself, and you can rely on it. First of all, I want to give the credit about the contents of this summary or little variation. So this document is a kind of summary and variation of this first reference, especially chapter 1. Dr. Schreier and Schaaf co-authored this excellent textbook for graduate students, and it contains a lot of interesting results in complex valued signal processing, not only complex valued vectors and scalars and vectors, but also complex valued continuous and discrete time random processes. So you can find around 80% of what I have told you from this textbook, even though some definitions and notations and some names may quite differ. However, what I want to emphasize is that you may not be able to obtain the fresh vectorization, related materials, p-fresh vectorization, fresh properization. Those things are my original research, and at the publication of this excellent book, the results were not well known or not yet published, so you may not be able to find these approaches. Probably you've already seen that this vectorization and properization makes our thinking very clear, especially when we have continuous time and discrete time random processes exhibiting cyclostationarity. So just by converting scalar valued random process into vector valued random process with some pre-processing, your flow of thinking may be greatly simplified, and your results may be explained very simply. Anyway, one of the reasons why I'm kind of covering this chapter 1 part very late in the semester is that sometimes we want to re-examine what we were doing from the beginning at the end. So that is the purpose of this review. So the first thing is that why we think about complex valued signals. Why? So first thing is this one. So suppose z, a random variable, complex valued, can be always written as the summation of its real part plus j times its imaginary part, then actually this complex valued random variable is equivalent to this real valued random vector, two-dimensional. And we know how to handle this one. As far as this mathematical equivalence is always true, why we bother ourselves to think about complex valued signals? So the authors of the textbook also wanted to justify why they published that book on complex valued signal processing. And so I grabbed some of their reasoning and also added my own, but very little, to justify. The first one is most important to me as an electrical engineer, especially radio wave application. So we are using antennas to generate electromagnetic wave, especially a radio wave. And the wave must be described by a phenomenon in 4 dimensions. One is the time dimension, and the other 3 is the 3-dimensional spatial dimension. However, what is also important is that whenever we use radio wave, not only the wave propagation phenomena, but also the input and output of the transmit-receive antenna is very important. Unless, in very extreme cases, our antenna input and antenna output have very interesting relation. What is that? The input can be viewed, it's not always true, but can be viewed as a real-valued bandpass signal, and output can be viewed as a real-valued bandpass signal. And between these two, we have linearity or linear superposition principle due to the wave phenomena. Of course, as I told you, on the extreme cases, these antennas themselves may induce some nonlinearity, which cannot be a part of linear superposition principle. Be careful. But in most of the cases, that is true. And what we know from our theory of analytic signal and Hilbert transform, blah, 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 we always can find complex valued baseband signal XL of t that up-converted to some center frequency, and when its real part is considered, then we can set that is the same as real-valued bandpass signal. So instead of handling a real-valued bandpass signal, we may very, very simply handle or think about complex-valued baseband signal. That is one of the most important reasons why electrical, especially radio wave communication engineers, think and handle complex valued signals. Another one is quite interesting. As you know, this time can be said as the era or period of FFT, the fast algorithm to implement discrete Fourier transform. Most of the wireless standards, not only cellular, but also Wi-Fi, adopts FFT algorithm to perform very fast computationally efficient DFT. And even though the input to the DFT block is real, the output is always complex valued because we think the frequency domain conversion, and whenever we consider that, we cannot avoid thinking about phase and magnitude or real and imaginary parts. So we cannot avoid this one unless access another additional property like symmetry, even symmetry, or other symmetry. Otherwise, we cannot avoid using complex valued signal once we work in the frequency domain. What would be the another reason? That is also very closely related to the first one, because in our digital modulation, we want to anyway generate a real-valued bandpass signal. And as we've seen already, real-valued bandpass signal has its equivalent complex-valued baseband signal. So what we do is that actually we consider a complex-valued symbol and possibly complex-valued symbol waveform that generates complex-valued baseband signal. Here, this Dn is from a complex-valued constellation. That's why we cannot avoid the use of complex value or complex random variable. And Also, this fourth reason is related to the bandpass signaling, because we not only have some frequency, center frequency, we also have phase term, so we cannot avoid that. Another one is that we consider complex valued signal processing is the Fourier transform. And as you know, if we have a linear time invariant system and input is with impulse response H, the output has its Fourier transform that is related as written here. So the frequency component at omega radian is scaled and phase shifted by the frequency response of the system, and that is the complex valued signal. Another one is also related to communication theory. We have use of analytic signal. In that case, even though the Hilbert transform has real valued input and real valued output, and its impulse response can be viewed as 1 over pi t, which is also real, we not only just use this Hilbert transform to save the frequency, we also add them up after we multiply j. So let's say input is s of t and output is s hat of t as shown here. Then we combine the input and the Hilbert transform output to generate the analytic signal that has in the frequency domain only non-negative frequency component. And this is the way to save the spectrum when people first started to amplitude modulation, because they immediately found that they were wasting bandwidth. Another one is also related to radio communication. As you see, wireless channel is better modeled in the complex domain, especially if you think about Doppler effect. It is very hard to handle it using in-phase and quadrature components, but very, very simple to handle complex valued some modulator that increases the each pass frequency by Doppler frequency, something like that. And they also talk about the multi-dimensional, multi-antenna signal processing, where slight change, slight difference in the path length from transmitter to different multiple receive antennas, slight change in path length arises the phase difference. That is kind of rotating the received signal from one antenna output to another antenna output. So even though you perfectly synchronize the phase of the first antenna output, all the signals in the other antenna outputs may be phase rotated version, which is a complex value signal. So you cannot avoid using complex valued signal and matrices. So it's kind of fully justified to use not only just the real and imaginary part, that kind of approach, but also handling the complex valued signal itself, very important. Got it? And whenever you talk about complex valued random quantity, this is kind of very interesting definition. The first one is that what is a complex valued random variable? And as I told you, it has jointly distributed real and imaginary parts. So here you can claim that Z is equivalent to two-dimensional real random vector. That's okay. Now, the problem is that unlike when we have real random variable, the first order moment and second order moment clearly defined. When we consider complex valued signal, we not only need to consider variance, but also have to consider pseudo variance or complementary variance. Why? Because if you just think about this one, how many parameters determine the correlation or covariance matrix, especially consider covariance matrix of this 2 by 1 vector. As you remember, the 1, 1 entry is the variance of the x, and 2, 2 entry is the variance of y, and the diagonal entries are some rho xy times sigma x, sigma y. So how many parameters do you have? First, variance of x, second, variance of y, and third, you have the correlation coefficient. The problem is that if you just focus on the variance of the complex random variable, you can immediately see that it does not have information about the correlation coefficient. Not only that, but also if you are just given the variance of complex random variable z, you cannot know which is the how much is the variance of real part and how much is the variance of the complex imaginary part. So you can never know. Interestingly, if you consider the notation is something wrong. Okay, just a second. Let me use tilde here. Ready? Yeah, okay. I forgot to. Okay. So let me see. Yeah. So as you see here, if you have additional information about the complementary variance in this case, then what can you do? Complementary variance is a complex number, so it has real part and the imaginary part. And if you just add the real part of the complementary covariance with the variance, what do you have? You have the information about the variance of x. And if you subtract information about the variance of y, and if you take care of this pure imaginary part, you can extract the correlation coefficient. So you have full information, not only in the mean is obvious, but also in the variance, and complementary variance contains all the information in this 2x1 real vector, random vector. That is the importance of complementary variance. The problem is that if you just take a look at the undergraduate level, especially textbooks about random variables and processes, they even do not talk about complementary variance. One of the reasons is that they usually assume this is zero. What does that mean? Actually, they named it as proper. So complementary variance ignorable when this information is zero. What does that mean? So first, real part is zero means that the real part of the complementary variance is zero, means that the real parts variance and imaginary parts variance are the same. That is the first one. Second one is that this correlation coefficient is zero. So what does that mean? Proper means real and imaginary parts has the same variance and they are uncorrelated. And that situation occurs a lot of times in very simple cases or some very nature-induced phenomena. However, especially in radio communications, that radio wave, unless it is generated by our sun or cosmic something, usually the signal, complex valued signal we generate as a complex baseband equivalent to the real passband radio wave does not satisfy properness or propriety condition. And as you see that the well-known DSB with carrier or transmitted carrier, that is not that does not generate proper signal, complex, when it is viewed in complex baseband. Anyway, so one of the simplest example is the difference between proper complex Gaussian random variable and improper complex Gaussian random variable. So let's compare these two. As you remember, when we have a complex valued random variable, properness means what? same variance and uncorrelated. And you know that the uncorrelatedness in random vector, real valued random vector, means independence. So in Gaussian case, real part and the imaginary part of that complex Gaussian random variable is independent. And not only independent, but also they have the same variance. What does that mean? They are, unless if you take out the mean part, then what? Real and imaginary parts, after removing the mean, are IID random variables, especially Gaussian. So you can use the Gaussian density definition, and after some simple manipulation, you can find this PDF, probability density function of complex Gaussian. When I first saw this one from the textbook, I was just thinking that the publisher made a typo. It is not. As you see, unlike the real Gaussian density, what do you have? In the real Gaussian density, you have square root, and not only the square root, you have what? You have 2 here, right? And you have just parentheses, not this absolute value bars. Of course, we can still use absolute value bars here for the real, but what does that mean? This is not just the squaring, it takes the complex conjugate and multiplication. And why these 2 disappear? Because as you see here, that the complex Gaussian's variance consists of real parts variance and imaginary parts variance. So if we assume real and imaginary parts variance, the half of the complex parts variance, then what? If you plug in this here, then you suddenly 2 disappeared. And also you don't have square root because what? You have real part and imaginary part must be multiplied together, and you have the same coefficient, so square root disappears. Now, let's see improper complex Gaussian case. There are too many improper complex Gaussian cases where you may have what? Different variances. Independent, but different variances. For example, you have the scatter plot of the real part of Z versus imaginary part of Z, something like this. So it's like an ellipse. Even in that case, we have independence between real and imaginary parts, but since their variances are different, you don't have the complementary variance vanishing, as you see here, right? So this is not vanishing. Second one is that even they have the same variance, unless they are uncorrelated, you have what? You have impropriety. So for example, you have something like this. Something like this. I'm not sure whether we really have the same variance in real and imaginary parts, but anyway. So this Gaussian case is very, very good example, but also it gives us some confusion because we have not only the propriety, but also have similar definition called circularity. Many people just believe circularity is the same as the impropriety, but they are different. Let me see. So here goes the, not only this, not just this one, just a second. Where is circular? Did I forget? Okay. Yeah, anyway, circular means that two things. Sometimes they subtract the mean, and sometimes they do not. Let's just assume we do not subtract the mean and just consider real circularity. So suppose you have a complex valued random variable z, and you multiply e to the j theta with some arbitrary theta. Then you have another random variable. And the definition of circularity is that if your PDF of z or CDF of z and that of z's theta is the same for all theta, then it is called circular. And this circularity is defined in terms of the distribution itself, not just the second order moments. So definitely this is a much stronger definition. And you can easily show that circularity implies propriety, but converse is not true. And these definitions of propriety and circularity can be extended to multidimensional complex valued random vectors. And again, they are quite different. Anyway, and here goes the most interesting part, which is not well known to most of the even electrical engineers, is the complex correlation coefficient. And let's see the definition. And it seems that there still is a typo. Why? Something's wrong. Oh, sorry, not here. In the numerator. So unlike our friendly Pearson correlation coefficient or simply correlation coefficient of two real valued random variables, we have complementary variance divided by variance, defining the complex correlation coefficient. And you see, this is much better than the correlation coefficient of two-dimensional real random variable. You may say that, hey, maybe this is the same as rho xy. That means the correlation coefficient between real and imaginary parts. Actually, it is not. This is better. You will see. Ready? First, let's see the denominator. Whenever we have a ratio, some neurons allocated to check the division by zero error, right? So when do we have this is not defined? When the variance is zero. But when the variance is zero, what does that mean? Real parts variance is zero and imaginary parts variance is zero. So actually it is a very special degenerate random variable, which is constant, right? So in that case, this does not work. Otherwise, this works. Even in the case, one of the components, real or imaginary, is really constant. Unless both are constant, it's okay. That's the good thing. And you may say that that also holds for this correlation coefficient. Why? Because after some manipulation, you can write it this way. But as I told you, there is a subtle difference. This requires both of the variances must be positive, right? But this is not, right? So there is slight better thing with the complex correlation coefficient. What else? What else do we have? So let's, even though I didn't write it here, let's remind us of the important results related to the real correlation coefficient between real valued, jointly distributed real random variables. So let me write down around here. So anybody remembers? First, how did we define the property? One of the most important property is what? This is always in between 1 and negative 1. Of course, it's real, right? Because by definition, it's an expectation of the product of two real random variables, right? So it is always real, and it is bounded by negative 1 and positive 1. And whenever we have inequality including equality conditions, we want to add something more, if and only if, especially equality holds. But we have equalities, right? Equalities hold if and only if blah, blah, blah. Otherwise, our inequality with equality condition is not perfectly or completely stated. So what do we have? When do we have equalities hold? In order to know this one, we need to first prove this one. And that proof really gives us information about these equality conditions. And anybody? Anybody remembers? So let's see the definition. There are many ways to prove the inequalities. The simplest one would be using your friendly, anybody, Schwarz inequality, right? So let's first try using Schwarz inequality. So this one is an inner product, as we interpret. So you remember the inner product of two real vectors. And if you square them, what do you have? You have A transpose A square root, just a second, 1, 2, 3, 4, no, not square root. No square root. And B transpose B. So we have on the left-hand side, 2 A's and 2 B's. On the right-hand side, 2 A's and 2 B's. And we have what? Equality holds if and only if A is proportional to B with some constant, right? So what do we have? If we apply this, rho xy magnitude squared is less than or equal to expectation of x minus mu x divided by sigma x squared, and the expectation of y minus mu y divided by mu y squared. And it is what? This is standardized x, and standardized y means that their second order moments are ones, right? So we have proved the inequality. Now, what about this one? Equality holds if and only if. So sigma x, x minus mu x equals some a times xy minus mu y sigma y, right? Because it's proportional to another one. Of course, there are two ways. You may put constant here, because anyway, proportionality means that. But still, you have both of the variance or standard deviations must be positive, so it doesn't matter. So what does this mean? The implication of this is very, very important, because left-hand side, you have a random variable. And on the right-hand side, you also have a random variable. So actually, this equality is what? This equality is almost sure sense. They are almost surely equal. What does that mean? From y, you can completely know x, and vice versa in this case. And now consider you write y in terms of x. Then what do you have? You have something like, let me see, let's use C. You have some ax plus b type of fine relation between x and y. And you can always see that Yeah, just a second. Where is correlation coefficient? Yeah, anyway, if you plug this one again here, if I remember correctly, you have something like this. So sigma x rho sigma x sigma y. So your dimension is, let me see, am I true? Yeah, I believe I'm correct. So another way is you have to have this relation. Got it? Just match the units. So you have here unit of x, and you divide by something with same units. So this is unit list quantity. Now you multiply something with unit of y, that becomes unit of y, right? So this is what you have. Now let's consider plotting a scatter plot. Then what do you have? You have here mu x, here mu y, and you have a straight line on which your dots lie on. Got it? And let me see. So if this is correct, then yeah. So your A can be 0 because this correlation coefficient can be 0. Got it? Yeah. So you have something like this. Just a second. Am I correct? No, just a second. Let's see. No, something sounds not correct. Okay, strange. Oh, okay, I got it. So this one assumes sigma x not 0. Okay? If sigma y is not 0, then you can have another form, if I remember correctly. But anyway, so you can have this form, y equals something, or x equals something form. And in most of the cases, both of the forms are equivalent, but in some special cases, I remember either one of the formula can be utilized. For example, suppose you have scatter plot on the line parallel to y-axis. In that case, you cannot use this one because you have no infinity here, right? You cannot have infinitesimally small sigma x, or you cannot have infinity just. Got it? So this form of affine relation between x and y has some problem. Especially you use y versus x axes. Got it? Now but anyway, what is important is that these two cases, what do you have? By the way, this 1 and negative 1 means just the sign of the coefficient A. Got it? If A is positive, then correlation coefficient is 1. A is negative, whatever value, A is negative, correlation coefficient is negative 1 when we have a affine relation between x and y. Got it? And as you see, if this is close to 1, then, when this is either 1 or negative 1, you have, this is positive, so you have different slope. When this is not 1 or -1, then you have dispersed scatter plot. Now, by the way, so this correlation coefficient is in many cases called Pearson's correlation coefficient, shows a fine relation, amount of a fine relation, or some people say linear relation between x and y. So if it goes extreme, linear or a fine relation becomes stronger. If it converges to 0, then they are independent or uncorrelated. Sorry, uncorrelated. Now, let's see this complex correlation coefficient and see the property. The first one is the proof that the complex correlation coefficient is complex valued, actually, even though here it is not written. Why? You already have seen that the numerator is the summation of real variance and imaginary variance. So it's real. But the numerator is what? The complementary variance may have real and also imaginary part. What does that mean? This correlation coefficient is what? A complex valued one. Got it? And then it says that its modulus, because we may say the compute the magnitude or modulus of complex number, is bounded. And this sounds nice. And as I just told you, we now want to check when do we have equality holding, right? So here goes the proof. I'm not sure it's correct or Gemini's hallucination. But anyway, you try, got it? So anyway, you can show it. And then we find, where it is? Yeah, we find the cases when we have complex correlation coefficient having magnitude 1. So if you see the proof, then yeah, as you see here, the numerators, sorry, just a second. Yeah, still something's wrong. Where is tilde? Just a second. Just a second. Yeah, seriously wrong. Okay. Okay. Okay, so definitely we have tilde here, then tilde here, tilde here. What is this one? Just a second. I'm not sure. Something looks wrong. Okay, you clear up. That's yeah, it's good to be a professor. You clear up the typos here. But anyway, so the Gemini claims, and I believe this proof itself is correct. Somewhere tilde disappeared. But anyway, so as you see here, unlike the real correlation coefficient, your equality condition holds when you have this equals 0. So either sigma sub x is 0, sigma sub y is 0, or sigma sub xy is 1 or -1. So this includes all the cases where your scatter plot is on the parallel line to y-axis, parallel line to x-axis, and any straight line on two-dimensional plane. Got it? So this is better in some sense. Got it? So whenever we have the scatter plot a straight line, then what do we call? This is a maximally improper random variable. So it's kind of, as you see here, it's kind of real random variable, just rotated in the complex plane and shifted by some complex number. That's why you see some claim here. So whenever you have a maximally improper random variable, you may find a related real random variable that is mu, a W here. And you move the center of this distribution to mu sub z, and you have some proper rotation. Sorry, something's wrong. Sorry about that. Yeah, something like this. Mu W. So you now have a zero mean random variable and rotate and shift. Got it? It seems there are a lot of hallucinations. Yeah, anyway. Now here comes the final, but what you already know result. So suppose we limit our processing of a complex random variable into an affine processing, or sometimes we just call it a linear processing. And linear processing of a complex random variable may be written in this form. So you generate a statistic y by multiplying a constant, could be complex value constant a to complex random variable z, and possibly you add some complex number b. This is an affine transform of z to generate y. And this is a kind of straightforward extension of affine transformation or affine processing of a real valued random variable to generate another real valued statistic. So you may call this is affine and this is linear and this is affine. The problem is that if we stick to this type of processing, then we have a serious problem in processing general improper complex random variable. That is shown here. So complex linear processing is insufficient in most of the times, and the authors of the book and also I say that we have information loss. And you can easily show that if we just use linear transform, we cannot exploit the information in complementary variance. That's just too simple. You have three parameters to describe the correlation between two random variables, variance, and correlation coefficient. The problem is that you cannot use the correlation coefficient information. So here goes the definition of widely linear processing, in which I differ kind of defining the term from the authors, Dr. Schreier and Sharp. And they say that widely linear processing of a complex random variable is just the same as linear conjugate linear filtering. So they just say that this is same linear conjugate linear processing. But I don't agree. And so I have written a little bit differently. So there are two widely linear processing. The first one is that you just take the real and imaginary parts, and you just affine process this two-dimensional real random vector by multiplying, so let's say, multiplying real valued matrix and add real valued vector to generate some real valued statistic. Okay? As I told you, a complex valued random variable is equivalent to two jointly distributed real random variables, and you know what is linear processing of 2x1 real random vector, or affine processing of it. So this is one of the most important approach in widely linear processing of complex valued signal. Why do I say so? Because you have here something like this. In order to get the real part, you need to add z and z conjugate and divide by 2. And similarly, you need to subtract z and z conjugate and divide it by 2j to get y, right? So here, you not only process z, you also process z conjugate by naturally transforming z into real 2x1 vector. Got it? And this is, I believe, one of the widely linear processing. And here, many people in this society named this one as real composite vector. So given z, this real imaginary parts written separately is called real composite vector. So real composite vector is linearly or affinely transformed. That is one approach. And nobody can argue suboptimality of this one because the mathematics says that that is the correct approach, but not unique. Here goes the second one. So people have paid attention to that one. Hey, anyway, we need z and z conjugate. So what about we just put z and z conjugate together and call this one complex augmented vector. So z is augmented by its conjugate. So sometimes it is called conjugate augmented vector. Got it? And what kind of matrix is going to be multiplied here? People claim that you multiply complex valued matrix and you add complex valued vector C. Again, something's wrong. So they are a little bit different. See that? Do you see? Here, even though each component or element of this real composite vector has z and z conjugate, your matrix is real valued, and here your constant vector is real valued. But here, you not only have complex or conjugate augmented component, complex conjugate, but also they claim that you need to use complex valued matrix and constant vector. It sounds something's wrong. Why do you feel that? You must feel this one. I felt that when I first saw it. Actually, this has redundancy. Just to see that, if you just take a look at this one, what is an equivalent real valued vector to this one? What is the size? If you are not informed that the second element is the complex conjugate of the first one? Probably you would say that 4 by 1 real valued random vector must be associated with that one. But as you see here, their imaginary parts are just the sign flipped versions, and real parts are the same. So unlike general 2 by 1 complex valued random vector, this type of complex composite complex valued vector 2 by 1 is what? Has very special structure. So something must be sparsified or something like that. That causes a lot of trouble. Actually, that was the reason why I could publish my results. Because if you take a look at the fresh properizer or properizing fresh vectorizer, actually, my former RA and I systematically removed redundancy so that the output of the transformer or preprocessor actually has very succinct description of the complex valued signal, even though my output is complex valued. So that was the topic of my recent struggle with my new RA called Gemini. And it turned out that it too much hallucinate, and I just write down my hope. Hey, can you prove this? Sure, blah, blah, blah. Sounds correct. So let's write a MATLAB and figure completely wrong. And after some debugging, I find that the original result is not correct. So I said, hey, what's wrong with this result, blah, blah, blah. And he said, suddenly, I'm sorry, something's wrong. Proof is not complete, and blah, blah, blah. So I really feel the humanity there, because my experience says that is the kind of ping pong relation or some phenomenon between me and human research assistants, former research assistants. So these days, LLMs become more human than before. Anyway, so here, I'm not going to talk too much about that redundancy, but that's very important. That's what I want to say. But in my opinion, these two are both widely linear, but in narrow sense. So most of the people just regard second approach as widely linear approach. So they just process something like this, rewritten in this way. So you have complex valued constant A, complex valued constant B, and you add these products. So if you ignore C, it's kind of linear transform of what? Z and Z conjugate. So it's linear, but it's not just linear in the sense that you have AZ plus B or C. So they call it linear conjugate linear. So linear, and here goes the hyphen or dash. Yeah. Linear conjugate linear or widely linear. So LCL is a term more, how to say that, preferred by Cyclostationarity Society. And for just the signal processing guys, widely linear, that terminology was more popular. But anyway, they are the same in narrow sense. Got it? And now let's extend the definitions and simple results so far to complex random vectors and random processes, especially that idea of widely linear processing. So suppose you have complex random vector, then what is a widely linear processing? Something like this. Okay? Or you may have double length complex augmented vector, and processing like this. Got it? What about when you have a random process, scalar valued? Same. Most of the widely linear or linear conjugate linear processes process this double length signal. So suddenly you handle vector valued signal. Same for discrete time case. Okay, here goes the circularity. So yeah, as I already told you. Okay. So the distribution of z times e to the j phi is the same as distribution of z for all phi, something like that. And as you see, propriety, blah, 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 does not imply circularity, but circularity implies propriety. Yeah. And it talks about the Gaussian case. Circularity is the same as propriety when mean is 0. Now, in order to move to the next topic, we don't have enough time, so let me just state something important. So consider the cases when you have maximally improper random variable or random vector. That maximal impropriety can be extended to complex valued random vector. Suppose you have a random vector to be estimated, but here B is maximally improper, especially all B sub i's realizations are real. Not only real, it could be, for example, 1 or negative 1 in BPSK. So suppose you have some BPSK symbols put together in B. The problem is that it's highly likely that you may have some special observation case where you have complex valued matrix H times B plus complex valued vector C gives you complex valued observation Z. Okay, so except B, all the matrices and vectors are complex valued. Now suppose you want to estimate B, the real valued, maximally improper real valued random vector B. We assume IID, blah, 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 for simplicity. In this case, you may still want to do something like this. So your linear transformation would look like this. And you know that this does not exploit all the second order property of some random quantity. In that case, you may have, just a second, not D noise, N, sorry. Yeah, something's wrong, just a second. Sorry about that, this is N, okay. Yeah. And you also may want widely linear processing of Z to generate estimate of B hat. Which one would perform better? Definitely, in general, widely linear approach generates better estimate than linear, especially when you consider the MMSE, mean squared error minimization. So given this simple mean squared error minimization optimality criteria, your widely linear receiver performs in general, better than your linear estimator. The problem is that, as you see, this is what? Something like this, block diagonal. The problem is that whenever you handle mean squared error minimization, you usually use orthogonality. In that case, you usually use something like this notation without having this diagonal structure. Am I correct? Just a second. Hmm. Yeah, I believe this is correct. Yeah. And interesting thing is that when you have maximally improper case, then even if it is random vector, as I told you, you can find equivalent, not just real case, you can find equivalent real random vector. So after some shifting and proper rotation. So interesting thing is that you may find actually the estimator in this form. So still, without this real part operator, you have linear processing. You just linearly process Z. But your optimal, in the mean square sense, estimator is linear real part of linear processing. So actually, even though you start from this form, you will have that one. When your target random variable is real. And if it is maximally improper, then you need to introduce some rotation, blah, blah, blah. But still you can show this is true. And that result is available from the textbook in some chapter. But I'm not sure whether we have time to cover that one in the next class meeting, which would be the last one. And as you've already done 3 midterm exams, and usually midterm exams are in-class exams, but we just put them as take-home. So we may claim that each take-home exam corresponds to each class meeting. So we can claim that, hey, semester is over. But still, unfortunately, we have last class meeting this Wednesday. So I'm going to find a good topic to be covered in the last class meeting related to our title of this course, Spectrally Correlated Random Processes. And we will have, again, the take-home final exam. And you will be given much longer time period so that you can manage the time with other classes' final exam. Got it? So you may expect the problem available from at least from this Friday. Got it? Okay, that's all for today.